All right, here are the solutions to the 3.9 activity on antiderivatives. So I reminded you of the definition there at the top. And the first problem here says write down 3 antiderivatives of each of the following functions. Not write down the most general, but let's just remember that, hey, there's more than one antiderivative for any function. So the antiderivative of 4x cubed, let's see, we raise x to 1 more power is the fourth, but we divide by 4. So we just get x to the fourth. So one antiderivative is x to the fourth. Or we could look at x to the fourth minus 100 or x to the fourth plus pi. Any constant could fill in there. Those aren't the only 3 right answers. Similarly, the rest of the way down here in number 1, the antiderivative of x to the sixth, add 1 is the 7th power, divide by 7 or multiply by 1/7. Put any constant you want on the end there. Same thing here for x to the 3 halves. We get x to the 5 halves, multiply by the reciprocal, which is 2/5. And then add any constant you want on the end there. Similar thing with cosine, its antiderivative is sine, plus or minus any constant you want to get the other 2 antiderivatives. Okay, number 2 says find the most general antiderivative, so this is when we're going to add a constant. So the first function is 3x cubed plus 6x squared minus 12x plus 2. So let's see, x cubed, we raised 1 power, which is the fourth. We divide by 4 or multiply by 1/4, so we get 3/4 x to the fourth. We get 2x cubed minus 6x squared plus 2x plus c. G of theta is cosine theta minus sine theta plus secant squared theta minus secant theta tangent theta. So these should all look like functions that you know the antiderivative of. You know which function has derivative cosine, it's sine. You know which function has derivative negative sine, that's cosine. You know which function has derivative secant squared theta, that's tangent theta. And you know which function has derivative secant theta tangent theta, that's secant theta. Add a constant to the end, and there's the most general antiderivative. Okay, h of t has some fractional exponents, and this is similar to the one of the examples in the introduction where we want to rewrite this thing so that we can use the power rule. So the first step here is just to rewrite h, not having taken an antiderivative. That's right here. And then go ahead and take the antiderivative. So t to the 3 halves is t to the 5 halves, 2/5 t to the 5 halves is the antiderivative. T to the 1 half, 2t to the 1 half has antiderivative 4/3 t to the 3 halves. We get minus 6t to the 1 half plus a constant. All right, 3 and 4 ask you to work backwards to actually find a function with some given information. So this first function is given that f prime is 12x cubed plus 3x squared minus 4x, and f of 1 is equal to 3. Find f. Okay, so we can step backwards to f. The antiderivative of 12x cubed is 3x to the fourth. Antiderivative of 3x squared is x cubed, and the antiderivative of negative 4x is negative 2x squared. We add a constant, and then we use our given information. We can stick with the red here. This is our given information. F of 1 is equal to 3. So we put that into practice right here. It says if you put 1 in for x, the output of the function is 3. And that allows us to solve for c. c is 1, and we can write down f of x. Okay, this next one is a little more challenging, number 4. It's reasonably long, so I wrote it all out here for you. We'll walk through it. You might want to pause the video and check it out also. So given that the second derivative of our function is negative 16 sine of 4x plus 4 cosine of 2x, that f of pi over 4 is 1 and f of pi over 2 is 2, find f. Okay, so let's see, we're starting with a second derivative. All of our given information is about f, so we have to step back to f prime, then we have to step back to f before we can use any of our given information. All right, so we have to think about this. What's it look like if we take the derivative of a function that looks like sine or cosine of something times x? We're going to have to use the chain rule. All right, so let's come back down here. I want to take an aside. If we take the derivative with respect to x of sine of 4x, what does that look like? Well, the derivative of sine is cosine at the inside function multiplied by the derivative of the inside function. So this derivative is 4 cosine of 4x. So if you want a function whose derivative is just cosine of 4x, you would need to multiply by 1/4. So that tells me that the derivative with respect to x of 1/4 sine of 4x, well, the only way that's going to differ is we're going to multiply by 1/4. 1/4 times 4 is 1, so that is cosine of 4x, which means when we step backwards here, every time we step backwards, whatever this constant is, we're going to have to multiply by its reciprocal out front. Okay, let's see how that happened here. Come back up here. In this first step, the antiderivative of negative sine is positive cosine of 4x, and then I multiplied by 1/4. So this 4 is 16 times 1/4. Same thing happens over here. The antiderivative of cosine is positive sine of 2x, and this 2, instead of multiplying by 1/4, in this case I had to multiply by 1/2 because of the argument going into sine to, in essence, undo the chain rule. Is 4 times 1/2. Okay, now we do that again, right? And then here we still have to handle this 4. So this 1 really that's here is 4 times 1/4. And this 1 that is here is really 2 times 1/2. And we get to f of x being sine of 4x minus cosine of 2x. This minus comes because the antiderivative of sine is negative cosine, plus cx plus d, two constants here at the end in our steps moving backwards. All right, now we got to put our given information into use. I guess I chose to put f of pi equals 2 into use first. So everywhere I see an x in f of x, I'm going to replace it with a pi, and I should get 2 as my output. So 2 equals sine of 4 times pi over 2, which is 2 pi, minus cosine of 2 times pi over 2, which is pi, plus c times pi over 2 plus d. And I evaluate those things, and I get c times pi over 2 plus d is equal to 1. Okay, now I play the same game at pi over 4. So I get 1 as the output is equal to sine of 4 times pi over 4, which is pi, minus cosine of 2 times pi over 4, which is pi over 2, plus c times pi over 4 plus d. And that simplifies. It looks like c times pi over 4 plus d is equal to 1. So now, let me get a different color. We have that this expression and this expression, they both are equal to 1. So I want to find c and d, so I can set those things equal to each other. When I do that here, I set them equal to each other. I can get rid of the d's from each side. I have c times pi over 2 is equal to c times pi over 4. Well, the only way that this could possibly happen is if c is equal to 0. Okay, and then once I know c is equal to 0, I can put that back into either of these equations above. So I chose this one here. Put c equals 0 in there. I get 0 times pi over 2 plus d is equal to 1, and d is equal to 1. And there we go, c was 0. So our function is f of x is sine of 4x minus cosine of 2x plus 1. And now, say we did all this work and we were like, wow, is that right? Like, did I actually do this right? All the algebra, everything. How do we check? We could check by, to check, find f double prime. It's going to require the chain rule. And it should be that if you take the second derivative of that function, you better get this thing back up here where we started. Otherwise, something went wrong in the process. Okay, see if you can use those examples to help you work through the homework in section 3.9.